Hi friends, in this class we are going to discuss another method that is uh, other than first we have discussed univariate method, right? Then uh, the next method which is in our syllabus is Powell's method. Powell's method, that means the method uh, which is used to, or method or algorithm, you can say both are one and the same. So algorithm, this is an algorithm which is used to uh, find the optimum value, that is minimize or maximize a function. Optimum value or optimum solution for the uh, unconstrained nonlinear objective functions or programming, or uh, unconstrained nonlinear programming problems. So we have Powell's method is here. Actually, Powell's method is an extension of the basic pattern search method. Pattern search method means, I think it is that is we have discussed pattern search method. If it is not done, no need to worry. Pattern search method and both way we will discuss. Okay, and it is the most widely used direct search method and can be proved to be a method of conjugate directions. Yes, this term conjugate direction method. This method is also known as conjugate direction method. So this term is very important that we are going to define what you mean by conjugate directions. Conjugate directions. Actually, these are directions only, or directions means vectors. Okay. For example, in an x1 x2 plane, x1 x2 plane, these are only directions. And the important thing, if you go back to your univariate method, there are two important things we have discussed, right? uh, Direction. For the optimization problem, we should get two things, that is direction in which you have to go. You should search. Okay, you should search so that the so that our objective function is minimized. And another important thing is how far you have to go, that is the step length, the optimal step length lambda star. Okay, this direction is very important. So uh, we have also said that from method to method only one thing is varying, that is the method which the direction, okay, the search direction is changing or find out. Only that way the method is having different names. Now we have conjugate direction. What do you mean by conjugate direction? Direction definition is that A, okay, A is a matrix of order n by n, and it is a symmetric matrix. Okay, and a set of n vectors or directions. Si, okay, that means we are considering a matrix A, uh, which is having an order n by n. So if n equal to 2 we are discussing, then it will be 2 by 2 matrix, that is like, for example, 2 by 2 matrix will be having A, K, B, C, D elements, and this column represents each vector. Okay, vector, this is a vector, AC is a vector, column vector, and BD is also again a vector. So that is the peculiarity of this matrix A. And a set of n vectors, the same n number of variables, a set of n vectors or directions. Vectors means direction also. that is denoted by set Si. Set Si. That is for n equal to 2, we have S1, S2. Okay. Two directions is said to be conjugate. Is said to be conjugate. More accurately, it is a conjugate. A conjugate we say if and only if Si transpose into A into Sj equal to 0. Okay, this is the for all I not equal to j, that is if S1 equal to S1, then these are two vectors, then one and the all same vectors, which means these are same vectors, so parallel vectors. So we are excluding the parallel vectors, but we are considering two vectors in n dimensional space, two vectors in n dimensional space. That is, if we have if we consider a three-dimensional space like this, like okay, like this, x1, x2, and x3 like this. Okay, then n-dimensional space, then the directions may be like this. Okay, infinite number of directions will be there, infinite number of vectors. Okay, and we are naming it as s1, s2, s3, etc., sn. Okay, so for every I not equal to j, and I varies from 1, 2, 3, etc. up to n, and j varies from 1, 2, etc. up to n, if the vector, that is s1 transpose into a, sorry, sim, okay, si transpose into a into sj equal to 0. If this condition is satisfied, then the si and sj, which are the two vectors, are said to be conjugate vectors. Conjugate vectors. That means we have, we have, for example, actually you should understand the notations very carefully. This si transpose into a into sj, this is actually a matrix multiplication. Three set of matrix are multiplied, right? So this matrix si transpose matrix means it is nothing but a column matrix. Okay, because a vector can be represented by a matrix, a column matrix, right? So if you take the transpose of that column matrix, then you will get a row matrix, right? So in that way you have to imagine. Okay, so if this condition is satisfied, then these two vectors are known as the conjugate vectors. Okay, then okay, this is the definition actually, and I will explain another special case of this conjugate direction. Conjugate direction. Okay, special case. Special case of conjugate directions. That is nothing but your orthogonal directions. Ortho orthogonality or orthogonal directions. Suppose in the previous our previous conjugate definition of the conjugate directions, if we put this A matrix, okay, A matrix equal to A matrix equal to identity matrix, okay, identity matrix, then what happens? Then the equation 1 becomes Si transpose into Sj equal to 0. This is nothing but your equation of your inner product equation. Inner product, that means nothing but Si dot Sj equal to 0. So this is our equation number 2. So what you will get? The condition for the orthogonality. So that means s1 s2, if we are taking two vectors s1 s2, then these vectors are orthogonal to each other, like your unit vector ax and unit vector ay, then its dot product is equal to 0. In the same manner, the conjugate direction is defined as this Si transpose, that is inner product along with this matrix, with a matrix A. Actually, this matrix A having n number of columns or n number of vectors, and these vectors are linearly independent. This C1 vector and C2. C1 and C2 vectors are linearly independent, and also it span the uh, space, span the space of dimension n, Okay, so that is the condition of this matrix A. Now this is the direction of this is the definition of conjugate direction. So why we define this conjugate direction mean? The direction is that for in the case of okay in the case of this Powell's method, basically the Powell's method uh, in the Powell's method we are taking the advantage of this conjugate direction. That means the search is going on in the conjugate direction in one way or the other, in one iteration or in another iteration. Okay, that is what that is why we have defined the conjugate directions. Now we will